So we're now going to begin to talk about the most foundational part of concurrency in Java, which are Java threads. And you'll get a chance in this lesson to understand what threads are and how they support concurrency. And concurrent applications very, very commonly use multiple threads to simultaneously run computations that often interact with each other, although they don't have to. Sometimes they do, sometimes they don't. One way to think about an easy differentiation between concurrency and parallelism is that parallelism tries to have little or no interaction between threads, whereas concurrency involves some interaction between threads. So threads are the most basic way of obtaining concurrency in Java. And a thread is essentially a unit of computation that runs in the context of an operating system process. And I think I described this earlier, but this is something that undoubtedly will show up on the quiz, so it's important to remember this. So you can see here we have a process, which is this little gray round angle, and in this particular example, we have one thread running inside of it. As I mentioned earlier, a process is a unit of resource allocation, management, and protection in Java. So it allocates resources, things like descriptors for sockets or synchronizers, memory, other kinds of things, and it protects the contents of one process are protected against threads running in the context of another process by low-level support from the operating system and the hardware in terms of something called a memory management unit, which you'll learn about if you take the OS course here. A Java thread can run on one or more cores during its lifetime, so it may start running on one core, run for a while, then it will typically be preempted, letting other threads run, and then at some point when it gets rescheduled, it could very well run on a different core. It's really up to the operating system to decide where to schedule the threads. Java enables multiple threads to run in multiple processes atop multiple cores. And this, of course, is all in the context of a computer, like my laptop, or my smartphone, or my desktop, if I had a desktop. So we'll see that there's other ways of doing computation that involve multiple computers, and that gets us into a whole other fascinating topic, such as reactive microservices, which are all the rage these days. Java threads that are running within the same process can communicate with each other using shared objects, also known as synchronizers, and they can all, which is this thing over here on the right that looks kind of like the little sharing icon. And then over here, you can also communicate by message passing. So you could pass messages between threads using thread-safe bounded queues or unbounded queues. Java threads in different processes can also communicate to each other either using shared memory, such as Android shared memory, or they can use so-called inter-process communication, IPC mechanisms. And good examples of IPC mechanisms would be things like sockets, and then there's all kinds of other things you can use. We will not talk much, if anything, about inter-process communication or shared memory in this course, although it's a very interesting topic. Now, traditionally, a Java thread, which I now designate with this slightly different visualization, is associated with an operating system kernel thread. There's typically, historically, been a one-to-one mapping between a Java thread and OS kernel thread, at least in the last 20 years or so. And that Java thread contains unique state, such as the ID of the thread, its name, which is different. The ID is typically a numerical value. The name is like George or whatever you want to call it. A stack, which is what these little round or little orange rectangles are. Priority, which says which thread gets preference over another thread if there are multiple threads ready to run. The current state of the thread, which is not the same thing as the state in quotes. The state is just the data or the storage information. The thread state says, is it running? Is it waiting? Is it blocked? And so on. So-called thread local storage, which is storage that's local to the thread. An instruction counter, which keeps track of where you are in your instruction sequence, your instruction stream, and any other registers like a frame pointer and so on. So that's typically what a Java thread has had for most of its existence. In Project Loom, which will be out hopefully soon, it's looming, traditional Java thread objects are now called platform threads. So a platform thread still has all the state we just talked about here. It has an association with an operating system kernel thread and so on. But the cool part of Project Loom, and this is really going to be quite interesting in terms of how it changes the way we think about Java concurrency, is that it defines a new feature called virtual threads, which are lightweight concurrency objects that can be multiplexed across one or more platform threads. So you can have platform threads, which are these guys over here that have their own stacks. in the operating system kernel. And you can also now have virtual threads with Project Loom. And then you can have literally hundreds of thousands or millions of these things, and they are multiplexed over a small number of kernel threads, or platform threads, as it were. So we may not get a chance to play around with this very much because, unfortunately, Project Loom isn't fully baked yet. So it doesn't come supported in Android, for example. In fact, it sadly may never be supported in Android for various reasons, but it's definitely going to be coming down the road with Java at some point. And you can play around with it. If you go to this link, you can get early access versions of Project Loom. And I'll show you some of this stuff later because it's really cool. Now, what I've talked about so far were primarily state or data that is unique per thread. So its thread stack is unique, its name is unique, its ID is unique, its thread-specific storage is unique, and so on and so forth. All the stuff that we listed over here are unique things. Each thread has its own version, its own priority, for example. However, there's also some state or data that can be shared across Java threads. And this is what we call common state. So examples of common state would be things like memory that's allocated in a Java virtual machine. So if you allocate memory, then if you put it in the right place and pass it around in the right way, then multiple threads can access that shared state. There's also other kinds of state that can be shared, things like static objects. If you have an object that's static, that means it can be shared by multiple threads. The minute you start sharing stuff, you have to open up a whole new can of worms and deal with synchronization. We kind of talked a little bit about that last time in the first class, where we talked about things like race conditions or situations where the loop would never terminate and all those kinds of good things. So we'll talk a lot about sharing, but keep in mind that there's two kinds of state: unique state and shared state. And it's a good idea to know examples of both, because that will almost certainly be a quiz question. So that's the end of our overview of Java threads, our introduction to Java threads. We're going to talk about a lot more stuff, of course, but I just wanted you to see the big picture. So the key things to come away with from this particular set of slides, this lesson, is that there are multiple kinds of threads in Java now, although you won't get a chance to be exposed to them right away, but they're coming down the pike. And the other thing to note is that threads share certain things and they have certain unique things, and threads always run in the context of a process.